The dawn of programming, machine code, and assembly. Programming in its earliest form was a far cry from the high-level languages we use today. The first computers, behemoths of vacuum tubes and wires, understood only one language: machine code. Machine code is a series of binary digits, zeros and ones, representing instructions that the computer's hardware could directly execute. Writing in machine code was tedious and error-prone. To simplify programming, assembly languages emerged. Assembly languages use mnemonic codes, short abbreviations that are easier to remember than binary sequences. For example, the instruction to add two numbers might be represented as ADD in assembly language instead of a string of zeros and ones. However, even with assembly languages, programmers still had to think in terms of the computer's hardware. Each assembly language instruction corresponded to a specific machine code instruction. This meant that programs written in assembly language were not portable. A program written for one type of computer had to be rewritten to run on a different type. Despite their limitations, assembly languages represented a significant step forward. They made programming slightly less cumbersome and allowed programmers to work at a higher level of abstraction. The rise of high-level languages, Fortran and COBOL. The 1950s saw a major breakthrough in programming with the development of high-level languages. These languages aimed to free programmers from the constraints of thinking in terms of hardware. Fortran, or Formula Translation, developed by IBM in 1957, was one of the first successful high-level languages. It was designed for scientific and mathematical computing. Fortran introduced features like variables, loops, and conditional statements, making it easier to write complex programs. Around the same time, COBOL, or Common Business-Oriented Language, emerged, targeting business applications. COBOL emphasized data processing and file handling, reflecting the needs of businesses at the time. Both Fortran and COBOL were significant because they were more human-readable than assembly languages. They used English-like keywords and syntax, making programs easier to write, read, and maintain. This improved programmer productivity and reduced the likelihood of errors. Algorithmic elegance, ALGOL, and its legacy. While Fortran and COBOL were successful in their respective domains, a new language emerged with a focus on algorithmic clarity and elegance. ALGOL, or algorithmic language. Developed in the late 1950s, ALGOL introduced concepts like code blocks, nested loops, and recursive functions. These features allowed programmers to express algorithms in a more structured and readable way. ALGOL's influence on subsequent programming languages was profound. Its emphasis on structured programming laid the groundwork for languages like Pascal and C. Although ALGOL itself was not as widely adopted as Fortran or COBOL, its impact on the field of programming was undeniable. It shifted the focus from machine-oriented programming to a more problem-oriented approach. This meant programmers could concentrate on designing solutions rather than wrestling with hardware limitations. A universal language emerges, the birth of C. The 1970s brought about the development of C, a language that would go on to become one of the most influential programming languages ever created. Developed at Bell Labs, C was designed to be powerful, efficient, and portable. It was initially used to develop the Unix operating system. C's combination of low-level hardware access and high-level programming features made it suitable for a wide range of applications. It gave programmers fine-grained control over system hardware while still providing abstractions for data structures and control flow. C's portability was a key factor in its widespread adoption. Programs written in C could be compiled and run on different computer systems with minimal modifications. This made it an ideal choice for developing software for a rapidly expanding computer industry. Section 5, Object-Oriented Programming, takes center stage, Java and C++. The 1980s and 1990s witnessed the rise of object-oriented programming, or OOP. OOP emphasizes the organization of code into objects, which encapsulate data and the operations that can be performed on that data. Two languages that popularized OOP were C++ and Java. C++, developed by Bjarne Stroustrup, extended the C language with object-oriented features. It allowed programmers to create reusable code components, improving code organization and maintainability. Java, developed by Sun Microsystems, was designed to be platform independent. It ran on a virtual machine, allowing it to run on any system with a Java Virtual Machine or JVM installed. Both C++ and Java became widely used in software development. Their object-oriented features enabled the creation of larger and more complex software systems. These languages also influenced the design of many subsequent programming languages. Section 6. Scripting the web, the rise of Python and JavaScript. The advent of the World Wide Web in the 1990s led to a demand for languages that could be used to create dynamic and interactive web pages. Python and JavaScript emerged as two popular choices for web scripting. Python, created by Guido van Rossum, emphasized code readability and simplicity. It became a favorite for web development, scientific computing, and data analysis. JavaScript, developed by Brendan Eich at Netscape, was designed to add interactivity to web pages. It allowed developers to create dynamic content that responded to user actions. Both Python and JavaScript were relatively easy to learn and use. They enabled a new generation of programmers to create web applications and enhance the user experience on the internet. These languages continue to be essential for web development today. Section 7. Domain-specific languages and the rise of specialization. As software development became increasingly complex and specialized, the need for languages tailored to specific domains arose. Domain-specific languages, or DSLs, are designed for a particular task or industry. For example, SQL, or Structured Query Language, is a DSL used for managing and querying relational databases. HTML, or Hypertext Markup Language, is a DSL for creating the structure and content of web pages. DSLs allow programmers to work with concepts and terminology specific to their domain, improving productivity and reducing errors. The development of DSLs reflects the growing specialization within software development. As new technologies and industries emerge, we can expect to see even more specialized languages designed to address their unique challenges. Section 8. Trends shaping the future of programming languages. The field of programming languages continues to evolve. Several trends are shaping its future direction. One trend is the increasing popularity of functional programming languages such as Haskell and Clojure. These languages emphasize immutability and side-effect-free functions. Another trend is the rise of concurrent programming languages like Erlang and Go. These languages are designed to handle the challenges of writing software for multi-core processors and distributed systems. The demand for languages that prioritize security and reliability is also growing. As software becomes more interconnected, languages that can help prevent vulnerabilities and ensure data integrity are becoming increasingly important. Furthermore, the development of new technologies like artificial intelligence and quantum computing is likely to spur the creation of entirely new programming paradigms. Section 9. Conclusion: the ever-evolving landscape of code. From the early days of machine code to the sophisticated languages used today, the evolution of programming languages has been marked by a constant striving for efficiency, readability, and expressiveness. Each new generation of languages is built upon the successes and learned from the limitations of its predecessors. The story of programming languages is a testament to human ingenuity and our ongoing quest to create tools that amplify our ability to solve problems and shape the world around us. As technology advances and new challenges emerge, we can be certain that the landscape of programming languages will continue to evolve, offering exciting possibilities for innovation and creativity in the years to come.